Right. So welcome everybody. We're honored to have like two Google data flow engineers with us today. They're going to do a live session, so it's not really a workshop, to show you all the works that have been done on having Beam run in Jupyter notebooks. I'm quite excited to see how that will work, because mostly I'm working in the Java part. So let's see how it rolls in Python and in the notebooks. So as said, like it's both Ning, Kang and Samuel Rohde, and they both work at the Dataflow team. So let's roll. Thanks.
Cool. Thank you, Alex, for that introduction. My name is Sam. I'm a software engineer at Google Cloud. I've been working on the Dataflow team for about 5 years now, and I had an internship during my university also on the Dataflow team. So I've been around for a while, and I've seen a lot of different parts of the stack.
Hi, my name is Ning. I've been working in Google for over 3 years. I've joined Dataflow team last year. So I've been working on Beam for over a year.
Great. I guess we can just kind of jump right in now. So this presentation was originally made to be kind of like an interactive way for people to really start to know what Apache Beam is and the different execution model and the data model that's kind of built in. I think might be the only kind of introductory course in this kind of Beam Summit for 2020. So I hope that you can learn a little bit more about the data model, execution model, and how to experiment on Apache Beam and prototype using the interactive runner. So first off, what is Apache Beam? If you go to the Beam website, you'll see that Apache Beam is an open source unified model for defining both batch and streaming data parallel processing pipelines. It's a long sentence and it has a lot of jargon, so let's try and break that down. Unified model means that you have the same API for both batch and streaming data pipelines. When a user comes from Spark, they may know that you have the micro batch. Oh, can you guys hear me?
Give me a second, because your audio is cutting itself a bit. I don't know if you raise the volume or something, or if everybody's being able to listen properly to Sam's audio. In that case, it may be me.
Yeah, we understand it's just a bit crackly.
Yeah, it's cracking a bit,
Yeah.
and probably it sounds like you increase the volume and it's cutting itself out a bit. I don't know. Could you try it again, Sam?
Sure. I'll slow down and enunciate a bit better. So the unified model, previous slide, please. Thanks. So if you look at Spark, and if you look at other different runners, they have different APIs for doing batch and live streaming or streaming processing. But with Apache Beam, you have the same API for both batch and streaming. Data parallel means that you have embarrassingly parallelizable data pipelines. So while you may have a million key value pairs, Apache Beam is able to cut those up into many different parts and send them to many different workers to be processed simultaneously. Processing pipelines, it may be slightly different than the pipeline definition you may be thinking of. Generally speaking, a pipeline from a data scientist or data analyst point of view means from the beginning, the creation of the data, to where it's stored and is being analyzed, that whole pipeline. But when Apache Beam is talking about a pipeline, it specifically means when you are loading the data, transforming it, extracting the data, transforming it, and then loading it somewhere else. But really, Apache Beam is much more than this simple sentence. Next slide, please. Apache Beam is really an abstraction layer. What that means is that while you can write your code in Java, Scala, Python, or Go in this application layer, it abstracts out the execution backend and the execution environment below it. So what this means is that you can write your pipeline once, and then you can pick how you want to run it. So if you already have a Spark backend, you can write your application in Python, and then you can send it over to your existing infrastructure. Let's say that you want to change your infrastructure from Spark to Flink, or maybe even to Dataflow. You don't have to rewrite your pipeline. All you have to do is just change your backend, just do like one little pipeline option when you submit your job, and then that's it. So Beam is really an ecosystem of different runners and this big abstraction layer that allows you to have the freedom to choose which runner and which language you want to write and run your pipeline in. Next slide, please. So some use cases that we've seen for Beam is that we've seen it do some really general ETL, some logs analysis. Event-driven processing is interesting because that utilizes Apache Beam's built-in streaming processing API. What you can do is that you can read from some topic, some like publisher-subscriber topic like PubSub or Kafka, and you can take one of those messages and you can kick off a lot of different analyses or loading from some other data store and then do more processing on that data later on. We have also seen, cool, thank you. We've also seen real-world use cases of ad engagement metrics, revenue forecasting, which we will go into a little bit as a demo later on, usage pattern analyses, and even utilizing Apache Beam as a platform. Next slide, please. So this question is asked a lot. And how does it compare with Flink? With Spark, how does it compare with Flink? And the real answer to that is Apache Beam is an abstraction layer, and Spark and Flink are individual runners. So while Flink may be an open source stream processing framework, right, it really focuses on streaming. Apache Beam can do batch, can do streaming, but the power that Apache Beam gives you is twofold. The same API for both streaming and batch, and the portability to run across languages and runtimes. Next slide, please. So now going into more of the nitty-gritty bits, the technical details. So what does Apache Beam execute? And there are three primitives that Apache Beam has. One is the pipeline, which is the overarching structure that holds the different transformations that you program into it. It's laid out in a directed acyclic graph, meaning that the transforms follow one another, but they never go back and loop to an earlier portion of the graph, to an earlier transform. In the graph, the nodes are called p-transforms, which is just a generalized way of transforming your data. It could be a map, so you could have a transform that it is applied to every single element in the pipeline. It could be a do-fun, a pardo, which means that you can write user code in your language of choice and write and have that execute on each individual element. Between the p-transforms, we pass something called a p-collection, which is essentially just immutable distributed data, right? P-collections cannot be mutated in any way inside a transform. What happens is that a p-transform reads a p-collection and it creates a new p-collection under it. Next slide, please. So here is Beam's data model. At the top, you have this p-collection, which is potentially distributed, right? Which means that it could be being executed on simultaneously on different workers. A P collection contains multiple windows, and those windows can contain individual keys. So a window is just a single time slice. It has a start and a finish, and it has associated elements, or a bundle, associated bundles within that window. Inside of that window, you have bundles, and inside of that bundle, you have multiple different elements. The key thing about P collections is that it also defines how it defines the sequential execution of the pipeline. So within each individual key, all those elements will not be processed in parallel. Those elements within a single key range will be processed sequentially. Next slide, please. Okay, and so now we are on the live demo portion. We have two demos. We have a batch demo, and then we have a streaming demo. And this will showcase how you can iteratively create a pipeline using the interactive runner in Python. Beam, Ning, why don't you take it away?
Yes, thank you, Sam. So the first example, if you can you see this notebook interface? Okay, nice. Okay, the first example will be a batch pipeline. We will explore data from computertracking.com. The reason we chose this data is because the data set is relatively small. We can use it as a demonstration because otherwise, if the data is too big, we don't really know if we're doing it right or wrong. So in Beam, there are two ways to get the data. One is you get the data through some API calls, get them in memory. Others is you just load them from files. So there are also two ways to get data from computertracking.com. We can get the JSON data from APIs. We can also download data in CSV files. So we have a batch pipeline utilizing either methods and as a demonstration. So the first two cells are setting up the dependencies to run this notebook. We can just skip them for now, since we already have everything installed in this environment. And now we define two functions. One is get JSON data from the API. The other is download CSV. And we can get the current data. And we can also download the file. And then we do some import. So normally when you're using the Python SDK of Beam, you only want to install, you only want to import Apache Beam as Beam and then import other transforms you might want to use. But here with a interactive Beam and notebook, we can import a module called interactive Beam. It has several utilities that you can use to run the pipeline interactively. And also we are going to use a different runner called interactive runner. It's basically a wrapper around some underlying runners. So when you use this interactive runner, it does some special things to make your pipeline executing a special way so that you can inspecting the pipeline and the transforms, the applications in it. So let's define a pipeline. So by default, we use direct runner as an underlying runner. We can create two P collections here. One is creating the P collection from the JSON file, the JSON we got from API. It's a JSON object in the memory already. We can also get it from by reading CSV files. And now we can see there is a utility called show. It actually visualizes data that you got in a P collection. So it tries to materialize the data in a P collection and convert it into a pandas data frame. It tries its best to convert it. Since this is a JSON data, it's already structured. It has all these fields. So you will see all these columns here. And you can do search in this table. We do the match. You change how many entries to display in each page, and this data is paginated. So we have 56 entries in the JSON data. That's basically because the data is copied to tracking cases for United States organized by state. So we have 56 data points. We can also take a look at the data we load in from reading a CSV file. we read the CSV file, it actually doesn't really know the structure of the data because your data is serialized in a text file, in a CSV file. So we'll see each row is just simply comma separated text in it. So if you're reading data from the file, you might want to parse it and put it in a structured way. So let's do that. You can write some read headers from the CSV file to get an array and use it to create a name tuple. Name tuple is something like a class. Once you get to this name tuple, you can do a parse step. So you can do a pardo using this pardo to parse it into structured data. Let's see. Oh, let's show the current data. Now you can see the current data is already parsed from the CSV file. And there are missing fields from the CSV files. So originally, if you get it from the API, it has NaN in it. But since we just parse it, the parsing doesn't put NaN in it. It simply has columns with empty data in it. And also, you can collect the materialized data as a pandas data frame. So here the data frame is collected and you call the data frames describe, and you can see this is a data frame. Another thing we can use with the show utility is that you can provide an option called visualize data. It actually tries to visualize the data with a library called facets. This library is used to visualize data for machine learning, but we think it's a good choice since we don't really know any of the P collections that you might write in your pipelines. We don't understand the data. So if there is a good way to generalize, a generalized way to visualize data, it would be great. So besides the data table here, we have the facets visualization. The thing about the visualization is you can actually choose a label. So here, let's do something. Let's look for the positive cases. And we can color it by positive cases. Let's see. Positive, where's the positive? Now we can see this is a data point with most numbers of positive cases. It will be state California, and these are the negative cases. So when you select a data point, it shows you the detailed information. You can also do scatter plot with this. Say if I choose positive as x-axis and choose negative as the y-axis. And actually, since we are showing this, it takes a while to display it correctly. Here, oh, nice, finally. So you can see now we have a correlation scatter plot with the column of positive and the column negative. Another thing you can do is binning. Binning is, you can do a binning against the positive column. And you can choose the count of the binning. It basically bins data into different columns. And you can see this one is being still California is being to the highest one. It just groups the data into different kind of bins. And later, this thing is basically analyze all the data points by columns in your P collection. Your data basically are categorized into numeric or categorical. Your digital numbers are numerical features. Your columns containing strings or states are categorical features. By looking at this graph, you can see how your data are distributed, and you can put them on the log axis. You can expand this. You can also see some useful information about the missing values, mean and standard deviation, zeros, %, mean, median, max, number of each column. And this is quite useful if you are not familiar with you don't have any insight of your data. So now let's try to find the MaxPositive. We already did that in the visualization. Let's do it in a Beam pipeline. Let's see what transforms can we use to get the MaxPositive. We wrap it all the data into a total ordering class where we just order all the data by the column positive. And you can just call show MaxPositive collection. What it does is actually executes a pipeline fragment that only produces P collection for you. So here we can see the maximum positive data row is this row, is California positive is this number. And we can do a total positive for today. And you can just show it. It would tell you the total. Basically use a map to get the positive number and combine it globally. This is a number, 5,074,749,000, sorry. And there is another data set that is historical data. So what we just saw was most recent data for a day. We can also take a look at all the data we have on the covidtracking.com. See what does it look like. It looks like this. So you can see actually some of the states we have multiple data rows because each row represents a day of the data. And then we parse it. Take a look at the data. Okay, this is historic data. In the table, you can click each column to order them. We can see there are many data rows with the same state. Yeah, that's what we expected. For demonstration, let's just take a look at this California throughout the timeline. So we can do a filter by state dew fund. And we can see what the CA data looks like. So now this P collection only contains California data. And we already went through that. We don't need to go deep into this visualization. Now we want to say, we want to find on what day the positive number increases the most. We do another total ordering to find the positive increase. And we can then get the date from the data set. And we can just call it the worst day. And now let's show it the worst. So it's July 22nd, 2020. This is a demonstration of how you can use the interactive beam in a node running a batch pipeline. I'll hand it back to Sam. Do you want to present, Sam, or do you want me to?
I can present.
Okay. Let me stop here.
Also, we have a couple of questions. I don't know if you want to address them now or maybe later. You guys decide.
I think we can address some questions now.
The first question is, where can we download notebooks to try them out later? Yeah, the open source version is already available in the Beam repo. So in the Beam repo, if you go to the SDK Python, let me see if I can type anything. If you go to the Beam repo, SDKs, Python, runners, interactive. SDKs, Python. Is that correct, Sam? Yeah, I think it's under this directory. So if you go there, there are instructions about how you can set up a locally started Jupyter Lab environment. You can also use something provided by Google Cloud. It's still in beta, but you can basically just start a VM and directly jump into a Jupyter Lab without installing all these things. Yes, the manager service is the data flow notebooks.
Yep.
Search
So
for
Nate
it.
asked, oh, sorry, go ahead.
Sorry, my screen went black. Yeah. When using the interactive settings, do you recommend using a small sample of data that fits in memory? Recommended to use interactive mode for doing developing, testing, then moving to a normal IDE when moving to production. Yeah, I think using a small sample of data first is a good way to validate your the correctness of your pipeline. Because otherwise, you will not know if you're building the correct pipeline if you don't really know about the data. To move it to production, so currently, yeah, everything is running in the direct runner. We plan to make it so that you can run interactively on data flow. Then you will be able to run with production level data. Yeah.
Yeah. Okay.
If anything you want to support.
How about we go back to the Jupyter lab for streaming now. So thank you for your questions. There'll be another Q&A session right after the streaming section. Can you all see this notebook?
Yes.
Yep, all right, great. So Ning showed the batch side of Apache Beam Interactive Runner, and I'll be showing the streaming side. In this example, we will be doing a really simple pipeline in which we read from Shakespeare's King Lear. This is a public pub/sub-topic from Google Cloud, and it just runs through all the different words from this book. The play. So first we import stuff. We set up the pipeline options to tell Apache Beam that we're doing streaming. We're giving it the auth for Google Cloud. And this option right here is specific to Interactive Beam. And what this tells Interactive Beam is that for streaming pipelines, what we want to do in order to enable deterministic replay for prototyping and iterative development of your pipeline, we say, okay, record 60 seconds worth of data from all the different sources in your pipeline. And you'll see what I mean in a second. So we create the pipeline. We start to read the words from the pipeline. And actually, we can do something like this. And what this does in the background is that it's starting up a pipeline that's specifically reading from this pub/sub-topic. And it'll read and cache all the data from that pub/sub-topic for a maximum of 60 seconds. And what this allows you to do is that it allows you to replay the pipeline again with the same set of data. So for example, if you have a pipeline that's misbehaving and you want to see how it works with a specific set of data, you can hook up that unbounded source to the pipeline, and you can run it through Interactive Beam. Interactive Beam will cache that data on disk, and then you can rerun the pipeline as many times as you want on that same set of data. This is really hard to do in a streaming setting because you have real-time data, and once you read that data, it's, depending on what you do with it, effectively gone. So now that we've shown all the data, this allows us to inspect this pub/sub-topic and the 60 seconds worth of data that we have read. So you can see we have read admin sound first, up to a total of 135 words in that 60-second window. So next up in our pipeline, what we want to do is that we want to count the number of words that occur within a given window slice. In this pipeline, we're going to be doing fixed windows, meaning every 10 seconds of wall time, we're going to be grouping up all those elements into a single window. Here we're doing windows of 10 seconds. It's windowed word counts. What it does is that it counts all the different elements that are the same and outputs a count. So you can see that there are a couple of more parameters that I added to here, which is include window info and visualize data. What the include window info parameter does is that it appends these three columns to the data frame. One is event time. So when this piece of data was ingested into your pipeline, the windows, which specific window this element is a part of, and the pane info. Panes are part of the more advanced features of the Apache Beam SDK. And what that allows you to do is that allows you to fire a given window multiple times. So you can buffer up elements, and then given some condition, you can fire that window now, and then maybe 10 seconds later, you can fire that window again. And each firing of that window is called a pane. Because our windowing is simple, only fixed windows of 10 seconds, that means that our window only fires once. And so we have a pane of 0. The visualized data is pretty interesting in a streaming pipeline. If we were recording, this would show you a live data of the elements coming in. So what you can do is that you can group up these windows you can group up the elements by the windows as they come in. So this allows you kind of a real-time view of the data coming into your pipeline, and you can use that for debugging or validation or anything else. And so you can even group up the x-axis as well. So window word counts .1, that is the count. So you can see that there is a panel, there is a group here in this window for 1 and 2. All right, so moving on, this window of lower word counts is essentially the same thing. And it allows you to, it goes through the pipeline and it takes a lowercase of the word. So this showcases that we really are caching your data from the pub subtopic. And we're just using that data and running it through your pipeline again and again every time you want to calculate something new in your pipeline. So you can see that all of these are in the lowercase, and their counts change depending on that. Like Beam showed also, is that you can take that P collection and you can materialize it into a data frame. So what this allows you to do is that it allows you to use any other tool that may be utilizing data frames. So you can use it with Matplotlib or something else to further visualize it, or for doing further calculations or quick computations based on that data. So this is the simple word count. Next up, I'm going to show you a slightly more interesting example. For this one, we have public data set up that shows fake taxi rides in real time in New York City. The point of this pipeline is that we're going to try and calculate the 10 seconds meter increment. So if you're a financial analyst in this company, you might want to know how much revenue you are making every X seconds, right? Every hour, but in this example, we're going to be doing every 10 seconds. So let's set up the imports, set up the auth and options. And then for this, we can do a capture duration of, say, 30 seconds. Let's create a pipeline. We can read from PubSub, and let's just see first what our data looks like. So like I said, this will be running in the background a pipeline, reading from this PubSub topic. And it's not just PubSub, you can also do it from any other unbounded streaming source. And it is caching the data on disk so that it can determine, it can enable deterministic replay later on. So in this data, we have ride ID, point index. So given a ride ID, it's kind of like, where is it in its travel? the lat longs, timestamp, meter increments, and meter readings. So these are going to be particularly interesting to us because we're trying to calculate the 10-second meter increments. So now in this window data, we're doing something different than the word count. We are doing a sliding window. Whereas the fixed window, it created fixed windows every 10 seconds. There was no overlap between the windows. Sliding windows means that there is overlap between the windows. In particular, for this one, it has a duration of 10 seconds, and it is being output every second. So there's going to be 9 seconds of overlap for each window. And that is, of course, configurable. So let's see what this window data looks like. So you can see here, we still have the windows, so when this was emitted, and the pane info. And final means that this was the final triggering of that window. So it looks like the windows look okay. Let's see the later windows. This one is at 2040 UTC. This was at, yeah, 40 seconds later, 30 seconds later, which was because we recorded 30 seconds of data at the beginning. So that looks good. So let's get the meter increment and see how that looks like before we sum everything up. So we have 930 entries, meter increment, given this event timestamp and these windows. We have a bunch of windows spanning all the way from 39 to 16. Yep, that looks okay. And so now to get the running rate per 10 seconds, what we can do is that we can do a sum, and that will look at all the different windows and group them up by window and sum up this meter increment. And so now we have our final answer. So this is meter increments per 10 seconds of sliding windows. So you can see at this time here, right, this window starting at 42, and with a duration of 10 seconds, we made around 1.89 cents. And this one is 2.26 cents. Or maybe it's in dollars, whatever that unit may be. Okay, and then if you want to, you can also collect that up in a data frame. So here the column 0 is the run rate, event time, and these are the literal objects from the windowing information. So in case you wanted to introspect instead of trying to do string parsing, you can take a look at these windows and use Apache Beam native objects for that particular thing. All right, and that is the end of our presentation.